to let me also share Dropbox links to the slides. I think David is going to put them on his website, but it might take time. Okay, very good. YouTube works. So it is my great pleasure to introduce the talk of David Vogan on, let me check the title to be absolutely sure. Okay, I'll let David to tell his title. You might.
So the title is Weyl Group Representations and Harish-Chandra Cells. And unfortunately, I looked at the slides in order to do this. And so this is going to cause a small, well, when I share the screen to show the slides, where did I lose? There they are. They are no longer full screen. And when I change to make them full screen, this will stop the sharing. But now I think if I share the screen, everything is okay. Oh, there. Oh. Except, oh, okay. What's wrong? Yeah, I can't. There we go. Okay, so I'm not going to give exactly the same talk that I planned to give. It's going to be much more about the background for the talk that so this is kind of an introduction to the talk that I was going to give. So it's almost entirely about other people's work from long ago, and maybe that's a good thing. One of my favorite compliments about a talk came, I was in Toronto and I gave a talk, and Lisa Jeffries had given a talk earlier in the day, and she said, "Oh, it's too bad our talks were in that order. Your talk would have been such a good introduction to mine." So I'm not sure whether this was meant as a compliment, but I decided to take it as one. So this is an introduction to the talk I might have given. So I'm having trouble advancing the slides, so this may cause grief. So I'm going to talk about a notion of cells of representations, which comes from Tony Joseph, and well, what cells tell you. I want to talk about what cells tell you about representations. So I'm especially interested in connections between representations and nilpotent orbits. So that's why the Springer correspondence is involved. And as I begin to say some serious things, I'll be quoting results of Lusztig. So that's the plan. And I guess clicking on the screen advances the slides, so I don't know how to go back. So I want to start with a real reductive algebraic group with a maximal compact subgroup, which is the group of fixed points of a Cartan involution. So all of these have complex points, and Harish-Chandra's one of Harish-Chandra's great contributions to the field was that the analytic theory of representations of G of R could, in many cases, be reduced to an algebraic theory of GK modules. So, well, I'm going to have a Cartan and Borel subalgebra of G, and then the Weyl group defined with those things. And I'm going to always talk about a dominant regular weight, and I'm thinking of this as defining an infinitesimal character for G, a character of the center of the enveloping algebra. And Harish-Chandra's results say that to study representations of G of R, you can study this category of GK modules of, well, infinitesimal character given by this weight lambda. So, of course, it's very interesting to study representations of singular infinitesimal character. But the things that I want to say today, it's easier to speak only about regular infinitesimal character. So these ideas certainly have consequences for singular infinitesimal character, but I just won't go there. So one of Harish-Chandra's basic results is that the set of equivalence classes of irreducible GK modules of a given infinitesimal character is a finite set. And so I want to look at this free Z module whose basis, you can have a basis of the irreducible modules, the Grothendieck group of the category of GK modules. And the Weyl group that I'm interested in is the integral Weyl group inside W. I think I'm not sure. It would be nice if I could scribble on the screen. I'm not sure if I'm going to try clicking this annotate thing, and all right. Just to practice, to see if this works. This is the set of. Oh no. I've chosen the wrong tool. I should have chosen this tool. This is the set of W in W with the property that W lambda minus lambda is an integer combination of roots. Okay. So okay. Sorry about that. Let me. Okay. Okay. So Joseph talked about highest weight modules, but it's exactly the same thing. Introduced a pre-order on irreducibles, and for Harish-Chandra modules, here's the definition that Y is smaller than X if there's a finite dimensional representation of the adjoint group, so that Y appears as a composition factor in this tensor product of X with a finite dimensional representation. So it's completely obvious that this is a pre-order, and so it gives an equivalence relation. So two Harish-Chandra modules are equivalent if you can get from starting from either one, you can get to the other by tensoring with a finite dimensional representation. And well, that lets you define an actual partial order. I should have said this was a partial pre-order. The strict ordering means that you can get from X to Y by tensoring with a finite dimensional, but you cannot go back. Okay, so now I can define Harish-Chandra cell. It's just an equivalence class of GK modules under this relation. So the cells are equivalence classes. Two things are in the same cell if you can get between them by tensoring with finite dimensional representations. And of course, these cells partition the irreducible representations.
David, I got confused about something very simple, sorry.
Sure.
Is it you fix the lambda?
Yes, lambda is always fixed here.
But F does, I mean, does it have, it could have a...
No, so in this tensor product, there will be many composition factors of different infinitesimal character. I should have said, I'm assuming at the beginning that X and Y are both irreducibles of infinitesimal character lambda. And so when you form this tensor product, there will be many composition factors of different infinitesimal characters, but I just ignore those. Okay. So I've broken up these irreducible representations into nice little finite sets. So how do Weyl group representations enter? So again, this is following Joseph. The integral Weyl group acts on this Grothendieck group. I'm not going to talk in detail about the definition. Again, it's defined using tensor products with finite dimensional representations. And a consequence is that you can use this action of W of lambda to describe the partial preorder. The description is that the way you tell that Y is less than or equal to X is that there's some Weyl group element, so that if you act on X by W, so this is some integer combination of irreducibles, and the statement is that one of the irreducibles appearing should be Y. Okay, so I'm going to write C of X for the cell of X. So this is a finite set of irreducible GK modules. This is the Harish-Chandra cell, and it's useful also to talk about C bar, everything which is weakly below X, and maybe even the boundary. And what's clear from these definitions is that in the action of the integral Weyl group on this Grothendieck group, the span of this cone is preserved. So W of lambda preserves the span of the cone, and it also preserves the span of this strict boundary. And so you can make it act on the span of the cell, which is the quotient of those two free Z modules. And so in this way, you get a representation of W of lambda whose basis is this Harish-Chandra cell. So it's reasonably called a cell representation of W of lambda. Okay, so let's see. So what's going on here is that the cells are making some connection between Weyl group representations and infinite dimensional Lie algebra representations. So what I'm going to do is explain what Joseph did with this idea for highest weight modules, and then what his results tell you about Harish-Chandra modules. And then what my talk was really supposed to be about, but we're up to probably 10:15 here or something, or sorry, whatever time. This is going to be close to the end. I'll talk about how Lusztig calculated Joseph's Weyl group representations on cells. So Lusztig's result is very explicit and complete. He says, here is a list of an explicit list of Weyl group representations, and these are the ones that appear on Joseph's cells. There's no such result about Harish-Chandra cells, but I want to talk about a conjecture for how to get such a thing. So, oh shoot. So what's written here is a link to some scribbles which give examples of Joseph and Harish-Chandra cells. I'm not sure. I didn't want to do this talk without giving some examples to give some hint of what this theory looked like. But and so if someone wants, I will go to this now and look through the examples. But I think if there isn't an explicit request, what I'll do is just continue on abstractly without telling you any examples. Is that okay?
David, I just wanted to say that you are welcome to use more than 1 hour. We are flexible.
Thank you. I'll try to keep the 1 hour, but anyway, the examples are there. So so what did Joseph do? So Joseph was looking at irreducible highest weight modules. So remember my lambda, oh shoot. Well, I have almost everything is wrong by a factor of the long element of this Weyl group. So sorry about that. So I'm looking at a set of irreducible highest weight modules indexed by, and this should be the integral Weyl group. And so in the case of the integral Weyl group, there are actually various relations, left cell relation, the two-sided cell relation, and the right cell relation. For the moment, I'll just say that Joseph partitioned this integral Weyl group into left cells and two-sided cells. So this LR equivalence has more relations than this L equivalence. So these two-sided cells are larger than the one-sided cells. And so he introduced this, again, this free Z module with basis a single left cell, and this is a left cell representation of W of lambda. And in the same way, you get this, well, this two-sided cell representation is actually a representation of W of lambda cross W of lambda. And the left action on a cell inside, a left cell sits inside here, and the W of lambda action on the left cell is the first factor in this two-sided cell representation. So what Joseph proved was that if you added up all of these two-sided cell representations, that's a W cross W representation, that what you got was the regular representation of W of lambda. And from that, it follows immediately that these two-sided cells give a partition of the irreducible representations of W of lambda. And these subsets are called families. The definition is you look at this two-sided cell representation, and it's necessarily a sum over certain irreducible representations of W of lambda of sigma tensor. Well, Weyl group representations are always self-dual. This is sigma tensor sigma. And what's also true is that as a representation of the first factor, it's W of lambda, then the two-sided cell is the sum of all these left cell representations inside it. Okay, so that's a lot of information, but there's more. So, what I'm mostly going to be interested in is understanding these sets of Weyl group representations. And the first thing that Joseph did was to prove that in this finite set of Weyl group representations, there's a natural base point. There's one distinguished piece in here. So that's his Goldie rank representations. One of the first theorems, it was, I mean, the reason Joseph was studying these things was to study primitive ideals in the enveloping algebra. And the first main result was that the annihilator of one of these irreducible highest, well, that the annihilator of one of these irreducible highest weight modules is just given by the left cell of W. Joseph was also interested in the associated varieties of highest weight modules. And this time, the statement is not if and only if, but at any rate, if two things are in the same right cell, then they have the same associated variety. And so here's Joseph's statement about a distinguished piece, he said in this left cell representation, there's a unique piece. Well, I won't say exactly what lowest degree means, but there's a distinguished piece which appears with multiplicity 1. And if you have two different left cells, C and C prime, each of them gives you a lowest piece, and the statement is that you get the same lowest piece if and only if these cells are in the same two-sided cell. So what that tells you is that these two-sided cells are sort of indexed by these special Weyl group representations, these Goldie rank Weyl group representations. And inside one of these two-sided cells, the number of left cells that you find is exactly the dimension of this distinguished representation. And in particular, the total number of primitive ideals of infinitesimal character lambda is the sum of the dimensions of these Goldie rank representations sigma 0. So say, well, these are Joseph's Goldie rank representations. And it turns out that Joseph's representations are the same set as what Lusztig had defined a few years earlier called special representations. So what do you see from this? That understanding the cell representations of W of lambda is absolutely critical to understanding primitive ideals in the enveloping algebra, and that they're at least helpful in understanding associated varieties of highest weight modules. So I'll say a little bit more about what the cell tells you about the associated variety. So I've got the same misprints written at the top of every page. So I want to fix a two-sided cell and its set of Weyl group representations. And inside there, there's this one distinguished representation. And well, now I am going to define what smallest degree means. So for any Weyl group representation, you can look at any Weyl group representation has to appear in the symmetric algebra of the Cartan. And so it appears in some degree, and you can define B of sigma naught to be the smallest degree in which it appears. So here's Joseph's theorem that this B of sigma naught is strictly smaller than B of sigma prime for all the other Weyl group representations in this family. Well, these are representations of the integral Weyl group W of lambda, but if you put that representation inside the symmetric algebra in this degree, and then just push it around by W, you get an irreducible representation sigma 1 of W, and this number for sigma 1 is the same as the number for sigma 0. This sigma 1 is actually one of, well, Springer had defined a correspondence which attached to every nilpotent orbit a particular Weyl group representation, and sigma 1 is one of the representations that appears by Springer's correspondence. So out of this two-sided cell, you get a nilpotent orbit. And this, what Joseph proved was that for anything in this two-sided cell, the associated variety was contained in the closure of this Springer orbit. So a more precise statement is that if you look at this orbit, nilpotent orbit closure, and you intersect it with, well, you can think of this, if you don't like to work on G star, you can think of this G over B dual as sort of the nil radical of B. So you take the nilpotent orbit and intersect with the nil radical of B, you get an algebraic variety which has irreducible components. And the statement is that the associated variety for anything in here is a union of irreducible components of this intersection. Okay. So this is really strong evidence that these Weyl group representations have a lot to tell you about the relation between infinite dimensional about the structure of infinite dimensional representations.
Sorry, could you
Yes,
please repeat, what is a Springer representation?
So I don't want to try to give definition, but Springer gave a map which starts with a nilpotent orbit in the orbit of G in the dual of the Lie algebra, and it produces an irreducible representation of the Weyl group. So in the case of GLN, the nilpotent orbit corresponds to a partition of N, and Springer gave a geometric construction that went from this nilpotent orbit to the symmetric group representation given by that same partition. So that's not an answer to your question at all, but I should say, nilpotent orbits were completely classified by Dinkin in the 1950s. Weyl group representations were completely classified. I'm not sure if it was finished in the 1950s or the 1960s. So these are, for classical groups, these objects have classical descriptions in terms of partitions. And for exceptional groups, there are tables coming from the 50s and 60s with lists of all of these things. And so Springer gave a geometric construction, and you can now look in other tables to find out how to relate the table of nilpotent orbits to the table of Weyl group representations. So this correspondence is described, what I find to be the most useful reference is the book of Roger Carter called Finite Groups of Lie Type. And well, I'm trying to decide. Yeah, writing on this doesn't seem very effective. So anyway, Carter's book called Finite Groups of Lie Type explains what this correspondence is and writes down in detail what the bijections are. Okay, other questions? Okay, so what do Joseph's ideas tell you about Harish-Chandra cells? So once you understand Joseph's definitions of cells, it's clear that for Harish-Chandra modules, this relation implies a containment of associated varieties. And in fact, it's not difficult to see that if you have a a strict containment, then you have a containment of associated varieties with inequality. And what's easy is that associated varieties are constant on cells. So yeah, as I say, this is just easy. The associated variety of a Harish-Chandra module is a constant on each Harish-Chandra cell. Okay, so this was using just brilliant ideas of Joseph, which are very easy, but then there are these deep theorems about Goldie rank polynomials, and if you apply those, what you find is that if you take a Harish-Chandra cell and you look at this W of lambda representation, that all of the irreducibles appearing in that cell belong to a single family inside W of lambda hat. And furthermore, inside that W of lambda representation, there is this Joseph's Goldie rank representation that has to appear. I think that's all I put on this page. So what do we got? So I said that the irreducible modules are partitioned into cells. Each cell has a W of lambda representation, and that W of lambda representation is assembled from the irreducibles in a single two-sided cell, and that it must contain Joseph's base point of that cell. And well, all of this gives you a nilpotent orbit. Once you have a nilpotent orbit, Costant and Rawless proved that if you intersect with G over K dual, you get a finite number of orbits of K. So this is analogous to what Joseph studied, the irreducible components of O bar intersect this thing. So Joseph's result about associated varieties on right cells, here's the analog, that if you take an irreducible Harish-Chandra module, that its associated variety is a union of closures of K orbits, well, of the kind that are written up here. And which union of closures you take only depends on the cell. Okay, so Joseph embarked on the program of calculating these associated varieties for highest weight modules, and I believe that problem is still unsolved, but you know, he does have this beautiful theoretical result that the answer is constant on right cells. So for Harish-Chandra modules, again, you have what the consequence of Joseph's ideas that the associated variety has this appearance, and knowing exactly what it is, you only need to figure out once on each cell. So let me proceed. So in the case of Harish-Chandra modules, there is a way to compute this associated variety, but it's really difficult, and I'm not going to say more about it. As I say, this problem is not solved for highest weight modules. It would be interesting, I think, to for somebody to look at this paper that I wrote with Jeff Adams and try to see whether you can make it work for highest weight modules. It's not obvious to me that you can. It's not an easy exercise, I don't believe, but it's possible. Anyway, so, well, we have this complex nilpotent orbit that arises from the Goldie rank representation of W of lambda. What happens is that if you know the other Weyl group representations that appear on this cell, they carry more information about X. And what I wanted to do was try to understand the additional Weyl group representations. So I said that this Weyl group representation, it's made out of irreducibles from a single family. So the first thing is to understand what a family of Weyl group representations looks like. So that's what I want to do next. And to start, I need to say a few more words about the Springer correspondence. So I said that Springer attached to each nilpotent orbit a Weyl group representation in a one-to-one, well, different nilpotent orbits give different Weyl group representations. So Springer actually did more than that. And I want to talk about the more part. So I've got this nilpotent coadjoint orbit. I want to take an element of the orbit. And so the orbit is G divided by the isotropy group. And the equivariant fundamental group for the orbit, I'm going to write A of O. What that is, it's the isotropy group divided by its identity component. The reason for the terminology is that subgroups of this equivariant fundamental group are the same thing as covers of the orbit that come with a G action. So here's Springer's theorem. To each irreducible representation of this equivariant fundamental group, you can attach a representation of W, depending on the orbit and a representation of the component group. This representation is always either irreducible or zero. And if the C is the trivial representation, then it isn't zero. So what I said before that Springer attached one Weyl group representation to each orbit. It's that one. It's the representation attached to the orbit and the trivial representation of the isotropy. If you look at just these non-zero Weyl group representations, then they're all distinct as the orbit and the irreducible vary. And every irreducible representation shows up on this list for a unique, every irreducible of W comes from a unique nilpotent orbit and a unique irreducible of the component group. So in this way, you partition the irreducible representations of the Weyl group into Springer sets, like this. So this looks a lot like families. I said the irreducible representations of W of lambda were partitioned into families. And well, this looks like that. And the two ideas are related, but they're definitely not the same. So this is the Springer stuff. So now I need to see how the Springer stuff is related to families. So Lusztig made a definition related to finite groups. If you have a finite group, he said you could look at pairs consisting of an element of the finite group and an irreducible representation of the centralizer of that element. And you look at these pairs up to conjugation by F. Okay. So now let me take one of these Joseph families of Weyl group representations corresponding to a two-sided cell. And remember that has a special representation in it, which is attached by Springer to a nilpotent. So there's another set of Weyl group representations, the Springer set, which is attached to the orbit. And I said the Springer set was not the same as the family. So here's what Lusztig proves. Suppose you look at the family intersected with the Springer set. So you look at the Weyl group representations that Springer attaches to O, which are also in this family attached to O. Then this A bar is called Lusztig's canonical quotient of the equivariant fundamental group. It's the fundamental group divided by the intersections of the kernels of all these representations Ci. So now we've got a finite group, and what Lusztig proves is that this family can be embedded in the finite set that he defined up here. That to every Weyl group representation in the family, you can attach an element of this canonical quotient and an irreducible representation of the centralizer of that element. And the way this works is that this Goldie rank representation in the inclusion goes to the pair 1 and 1. You take the trivial element of A bar, whose centralizer is A bar, and you take the trivial representation of A bar. So that's what corresponds to sigma 0. And if you look at these Springer representations in the family, then what they correspond to is the identity element of A bar and the representation Cj. So this is really hard to get your head around, I think. I'll just say where this came from in Lusztig's work. Lusztig was interested in studying unipotent representations of finite Chevalley groups. And what he proved was that unipotent representations came in families. These are the families of unipotent representations are very closely related to L packets. But you take a nilpotent, one of these nice nilpotent orbits coming from a two-sided cell, and then this entire set, M of A bar, parametrizes the unipotent representations attached to O. I've said that terribly. Actually, I am, to try to redeem myself, gonna try to write the idea at the bottom of the page is supposed to be that a Langland's parameter for a unipotent representation of G of FQ is actually, I'm going to write O check and X, where this, let's see. Well, I don't know. This O check is this is a complex nilpotent orbit in the Langland's dual group, G check, which is dual to O, and this X is in A bar of O check, and then, you know, when you talk about Langland's parameters, the component group of the centralizer of this Langland's parameter is A bar of O check upper X. And so an irreducible in the L packet is supposed to correspond to this C in A bar upper X hat. This is, so I've certainly made the page uglier. I'm afraid I probably didn't make it any clearer in the process. But this is meant to give some idea about why a ridiculous set like this M of F ought to have anything to do with representation theory. And well, so Lusztig's result about unipotent representations you can think of as a version of Langland's classification for finite Chevalley groups. Okay, so well, Lusztig is classifying unipotent representations. What happens? I have to stop doing this. Okay, and the last point is that the irreducible representations of W are naturally included in the unipotent representations of the finite Chevalley group. So that's how you get the theorem, which is here. Okay, that's kind of nasty. Let's see what I can do in the last 5 minutes. And any questions about this? I'm sorry, it's such a.
So, I don't see where does the dual group appear.
So in Lusztig's result, this in Lusztig's result, this nilpotent orbit is in the dual group. And I haven't.
So
this group, I mean, I described this A bar in the theorem in terms of nilpotent in G, but it turns out that you get the same A bar if you use the dual nilpotent in the dual group.
I see. Thank you very much.
Okay. Okay, I'm probably going to have to erase all this nonsense. Okay. Okay, so there's this set attached to a finite group. One way to think about this set is that these are conjugation invariant coherent sheaves on the finite group F. To give a conjugation invariant sheaf, well, an irreducible sheaf is going to have to live on a single conjugacy class. So it's going to live over the conjugacy class of X. And if it's going to be an equivariant sheaf on the conjugacy class, that's given by an irreducible representation of the isotropy group. So now if you have a subgroup of F, you can look at the constant sheaf on S. That's certainly S equivariant. And so you can push it forward to an F equivariant sheaf on the F conjugates of S. So this is, I'll just do this quickly. The point is, this M of F is talking about irreducible conjugation invariant sheaves. What I'm saying is that if you have a subgroup of F, you can make a natural conjugation invariant sheaf, and that sheaf must be an integer combination of these irreducible guys. So this number here is the multiplicity. So this construction goes from a subgroup of F to a non-negative combination of elements. And well, this is what it is. And I'm going to skip that. So here's well, I'm out of time. So what do I want to mention? I'll just mention that what Lusztig proves is that, you know, these families of Weyl group representations sit inside his finite sets M of A bar. And what he proves is that for any left cell, you can find a subgroup of A bar with the property that the multiplicities of Weyl group representations in the left cell are given using that subgroup in a very simple finite groups way. And Lusztig tells you exactly which subgroups turn up. One of the subgroups that turns up is the whole group A bar. And in that case, the cell consists of the Weyl group representations always attached to, well, a conjugacy class in A bar and the trivial representation. And there's also a Springer cell in which this subgroup is trivial, and the corresponding cell is just the sum of the Springer representations that appear in the family. But he tells you exactly what's what. And so that's the end of the introduction, and therefore the end of my talk. But I'm skipping the examples. What I wanted to hope, well, theorems of Monty McGovern and Byrne-Binegar tell you that lots of Harish-Chandra cell representations are given by Lusztig's construction, but sometimes you have to use not one of Lusztig's groups. And so what I had intended to talk about was the conjecture that any left cell, any Harish-Chandra cell is given by a subgroup of this A bar in a way that I wanted to discuss. Anyway, that's the end of the introduction, and so the end of the talk, and thank you for your patience.
Thank you very much. Questions, please. So, David, maybe you can tell us this slide at least.
So, what McGovern did was, he said, if you take a real form of SON or SP2N or anything in type A, then a Harish-Chandra cell was isomorphic to one of Lusztig's left cells. And what McGovern also showed was that if you went away from classical groups a little bit to spin and the projective symplectic group, that there were Harish-Chandra cells that were not Lusztig left cells. So what, well, what I was originally trying to understand was these Harish-Chandra cells, which McGovern proved were not left cells. I was trying to understand what they were, and I haven't done that. And say that what Byrne-Binegar's contribution was to look at all of the real exceptional groups, all coverings, everything, and to see that in those cases, the Harish-Chandra cells were really isomorphic to left cells coming from the Weyl group theory.
David?
Yes.
So a lot of what you told us is somewhat old. I mean, 20th century kind of results. Could you summarize, sort of, just sketch for us, or what the more recent developments are? So I mean, just so we can separate.
Sure. The more recent part was going to be entirely conjectural. It was going to be how you attached, well, I mean, the conjecture that's stated here, that always a Harish-Chandra cell can be described by a subgroup of Lusztig's A bar, but then I was going to talk about the conjectures for how you related this subgroup, understood this subgroup geometrically in terms of the real form. I'll mention so here's a result which that is more or less Jeff Adams, that if you have a complex nilpotent orbit, and you want to know what real forms that complex nilpotent orbit has, then you should look at the isotropy group for the nilpotent orbit and count the conjugacy classes of elements of order 2. That statement is imprecise and incomplete, but it's close to true, and it's a very nice thing. So counting conjugacy classes of involutions in algebraic groups, this is an old and easy problem. Well, it's an old problem, which is well understood, and that's tied to understanding real forms of nilpotents. And this was supposed to be a piece of understanding these Harish-Chandra cells.
So would it be fair to summarize your talk as ideas for going beyond the 1980s?
No, I mean, the summary of the talk is that it was all about the 1980s, I'm afraid. So you know, I mean, well, the reason for it was that I think it's possible to go further in those directions, but I didn't do that.
Okay, thank you. Thank you.
Let's thank the speaker again. Or maybe there are some further questions. Okay. So David, if you ever want to give the talk to which you just gave an introduction, you are most welcome to do so.
Thank you.
We will be happy to hear. So we have a free slot in 2 weeks.
Thank you.
Next week, we will have a talk by Paul Nelson on the orbit method, microlocal analysis, and applications to L functions. Everyone is welcome.
Thank you again for the invitation.